Hi everyone, my name is Giacomo Fenzi, and today I'm going to be giving a talk on category theory. The idea is we're going to be starting from the very basics, so I assume no prior knowledge of category theory, and we're going to be building towards the understanding of some of the mathematical structure and mathematical definitions that underlie some of the most important type classes in Haskell. So we're going to be talking especially about functor and applicatives. But in this talk, I'll also be talking about monads. I'm not going to really go into the type class definition of Hask in Haskell of monad, but we'll just because it follows very closely from what we have. So I will not be touching that too much. We will just be working like that. This talk, the idea is that I'm going to try to work through the definition and work through everything that I talk through on paper. We'll see how that goes, because of course, live talk and live math is not exactly the easiest thing in the world. So we'll see how it goes, and hopefully we don't have too many technical hiccups. So I wanted on this first slide to give you some idea of the kind of thing that we're going to be looking at. So we're going to be starting from some motivation, of course, which is always the best thing, because you always want to find out why you're doing stuff. Then we're going to be starting with a definition, as everything does in math. So we're going to have the introduction of categories, and some basic facts about them, some basic examples. I'm going to try to complement it with some examples, which might sometimes include some knowledge about other fields in math. For example, I very much like the group theoretic examples, or those with rings and those with vector spaces, but it is not necessary. I think I'm going to also make some very simple examples which should be able to be understood without any mathematical knowledge. Hopefully, that's always a bit of a tall order. Then once I've talked about categories, we're going to be talking about isomorphisms, which are our way of telling the two things are really the same. Then we might be talking about functors, which are ways of mapping between categories. We're going to be talking about natural transformations, which are ways of mapping between functors, which is fun. Then we're going to be talking about something which are called universal mapping properties, which are essentially they are object-free way of defining objects by their property, which makes the object then unique up to isomorphism, which we'll figure out what all these talks are. I'm just wanting to give a little brief overview. Then we're going to be starting to going where we really want to be, which is monoids and monoidal categories, which essentially they are the very simplest structure that you can build in an algebra sense. Well, there's something which is even less structured, but honestly, if you ever want to do something with them, that you're probably going to be starting with a monoid. You don't want to touch magmas and all these things which are before, because they really don't give you that much. Then we're going to be talking about monoids in a category. This is a very common pattern in category theory. You take something which is usually defined with set theory, and then you just move it into a category. You're like, cool, what if I replace all these things with this function with arrows? What would I get? So this is a very common process. And we're going to be talking about monads, which can be very easily expressed in the same sense. Here we'll introduce the category of functors, well, the category of endofunctors to be more precise. And then we're going to be talking about monoidal functors, which are functors which have the additional property of being preserving the monoidal structure of a category, which is going to be interesting. And this is exactly what an applicative functor is. And finally, we're going to be just drawing some parallels and seeing how things are in Haskell. So the idea is there to tie all back and see why the things in Haskell were tied that way. So hopefully the talk will be interesting. And I'm going to start with some motivation. So first of all, why category theory? Well, category theory is one of the most, I would say, compelling and innovative ideas that were done in the 20th century of mathematics. They are a very general tool that can be used to prove things in a very wide variety of fields. And the idea is that the way that these proofs are presented is very natural. In some sense, it is the most natural way possible. So it allows you to both prove a lot of things. It allows you to prove them beautifully and to get very general and very abstract results. And in fact, And categories, especially those which are more extended, like infinity category and stuff like that, can also be used for a lot of things. For example, there's a very beautiful connection with dependent type theory and all this kind of stuff. So in a sense, it is a very useful tool. It is quite interesting because it is something which was initially kind of weirdly received. Like I would say, like category theory is now sometimes called affectionately, in an affectionate way by mathematicians as abstract nonsense, because essentially in a lot of applications you just keep drawing arrows until you follow around diagrams until you get to what you want. So it's a very interesting and beloved field, which can feel very abstract and out of touch, which is interesting. That's the kind of stuff which I like as a pure mathematician aficionado, I would say. So that's kind of the motivation. It allows you to prove everything that is obvious very easily. Often, like because in category theory, you kind of like exploit the structures of the function between things that you're working with, which yields those beautiful proofs. But it is very hard to prove non-trivial things. So, for example, number theory is a field which I don't think has got much overlap with category theory, simply because to prove those relations, you need to actually look into the objects. And in category theory, we will see you have your spaces, your objects, your groups, whatever, and you don't look into them. You just look into arrows between them. The slogan of category theory in a certain sense is that it's all about the arrows in a way that we will make precise quite soon. So, all right. So yeah, I had to change because there were a couple of hiccups and it took me 2 days to figure them out. So let's continue with the talk now. As everything in math, we're going to start this talk with a definition. In particular, we're going to start with a definition of what a category is, right? So let us start with this. Hopefully this will work now. So definition. So a category, we can think it as three main things. First of all, we have a collection of objects. So I'm just going to write that down. And these objects, you can think of them as kind of like the sets in set theory, right? So these are is something which I do quite often. In order to understand why a categorical definition is like that, it often kind of really helps to think about set and then apply that to other categories. That is it, because set has got a lot of very nice property. It is Cartesian complete. I think it is co-Cartesian complete, and a lot of other things which I will not delve into, which essentially makes it very nice from a categorical perspective, which is compared to some other categories, such as, for example, the category of fields, which are just awful. So category, think as set, so with object as set and arrows as functions, and they should kind of bootstrap your intuition. So these objects, I will represent them as points, kind of like this. So usually give them a name like A, B, C, D, something like that. So collection of points. Then we will have a collection of arrows, which I will mostly call them arrows, but I might refer them to as morphism as well, because that's the most technical names. How do these work? Well, in the very obvious way. So an arrow is something which is between two objects. So between A and B, we might have an arrow F, for example, which we will also write for more concisely, F goes from A to B. So these are the arrows. Cool. Now, as any kind of abstract mathematical definition, we would like to define how these arrows and these objects interact with each other. And so we have an operation which we just refer to as composition, which is still think about set. It's similar to the composition of functions. So, so composition. And I will write it as a dot, or sometimes not write it at all. This is quite common. It just makes things a bit nicer. So, for example, composition is not a total operation, so you cannot compose any kind of arrows, which is equivalent to how you cannot compose any kind of function, right? So if you have a function from apples to pear and one from oranges to, I don't know, kiwis, then you cannot get a function from pears to kiwi by putting them together because they don't really match. So when does this thing match? It is when the target of one arrow matches with the source of another arrow. So we can write this like this. So if we have a function f from a to b and a function g from b to c, then there is a composite which we write as gf, which goes from a to c. You might notice that I have omitted the operator because it just makes it a bit nicer. Like if you want, you can add it. It just doesn't really add anything. Right. So again, just think about composition in a set. This is kind of the idea. What properties does this kind of operation need to satisfy? Well, for a category to be such, you need to satisfy two main properties. So the first one is associativity. Well, technically, we could say that it needs to satisfy three, because we need that GF is an arrow of the category. So, and this, some people might consider that as a closure property. I don't particularly do, because I think of the composition as a function from the arrows of the set of compatible arrows of the category to the arrows of the category. So I think it is closed by definition, so I don't need an extraneous condition, but some people do. So just wanted to mention it out. So again, we need associativity. We could write a diagram for this, but it just gets a bit messy. So I write it in symbols. We suppose we have three composable arrows. So we have maybe f from a to b, g from b to c, and h from c to d. I still know my alphabet. Then we require that fgh is equal to fgh. So wherever you put the parentheses, you still get the same thing. So since there is, by associativity, there is no possibility for ambiguity, then we will just say that we will just write it fgh and don't clutter everything with parentheses, which is always nice. Cool. Okay. So the second thing that we need for categories is identities, and how we formulate them. They behave exactly like the identities on sets. So these are the functions which do nothing on set. So I just write the axiom for them. Identities. So for every object A, we will have an identity which will be denoted by 1A, which is an arrow from A to A. So if the object A is like this, the identity will go to itself, and it will need to behave well with respect to other arrows. So for example, if we have any other arrow like F from X to Y, then we will have that, well, I'm just gonna write this so I don't mess up the orientation. So if we have F from X to Y, this is gonna be 1X, and then we can have 1Y over here. And the condition that we need to satisfy are the following. We're gonna have that F, so 1X followed by X will be equal to F, and that's gonna be the same as, so this is Y and this is 1Y. It's gonna be the same as 1Y followed by F, right? So that's the idea. These identity functions don't do anything. These identity arrows don't do anything. And so this is gonna be the only action that we require for the category. So now I have two notes to make. The first one is that it is more of a philosophical almost. Well, I wouldn't say philosophical. It's more of an idea of a mindset that you need to get into to work with categories. And the idea is something which I mentioned before, is that everything is all about the arrows. When you're working in category theory, it is very important that you don't look into their objects unless it's absolutely necessary. All your definition, all that you do should only be done in terms of the arrows and nothing else. So this is what gives a lot of the power of category theory and what gives it a lot of its beauty, because the proofs which only use arrows instead of the inner structure are just very, very elegant, especially if you start working with multiple categories and all of the jazz. So that's the first important thing. The second one is more of a pedantic note, and that goes to speak of the terminology which I was using. So before you know that I defined a category to have a collection of objects and a collection of arrows. If you're more used to other mathematical definition, you might have wondered why I didn't use the word set in here. That is because there is a small but important difference. In set theory, there are some kind of sets which you can reasonably describe, but you cannot really express because in set theory, because they would bring toward contradiction. One of them, for example, is the set of all sets, which is very easy to prove that it cannot exist in set theory because it contradicts some properties regarding its subset and the power set. So essentially, these kind of restrictions are things that when you do normal mathematics, I would say, you don't really get into and you don't really mess with at any point, because whenever you work in there, everything is defined in terms of set. So it is very hard to build a set which is too big in a certain sense. So in category theory, instead, these kind of things happen quite often. So you can have categories like the category of set whose collection of objects is actually all the sets. So it would be, if I were using the word set, this will be the set of all set, which is a contradiction and it cannot exist. Similarly, you can have categories in which the arrows between two objects are more than a set in a certain sense. And so that's why we need to use this term collection instead of set. So this might, if you're like very formally driven, this might sound very weird to you, but I assure you it has been formalized. There isn't any problem. If you're looking for the actual formulation of it, I suggest you go into McLean's book, Categories for the Working Mathematician, and there he spends a chapter just building up an hierarchy of sets, which can be used to formalize this concept in a correct way. Essentially, the main idea is that you build small sets and large set, and then you build an hierarchy, and you do hierarchies of categories as well. So that's kind of the idea. Anyways, this was the definition of a category. Now we can go and see some examples. So let's go with that. I'm gonna just draw some points. So I'm gonna draw 4 points. I'm gonna start drawing some arrows between them. So I'll just do something like this, and then I can make this into a category. So technically, this is related to essentially the free category on a directed graph, but I digress. So how do we make this into a category? Well, first of all, we need identities. So I'm going to just put identities on every object, because that's something that we need to. Then we need composites. So for example, you see that this and this need to have an arrow which commutes. So I'm just going to connect these two, right? Same for this and this, which need to commute. And then we can say that there is an arrow from here to here. In fact, there could be, in this case, there could be many different ones, but we can just put some conditions on it to make sure that we don't get too many arrows. Like it's kind of interesting. Like this kind of construction can yield very big categories in some sense. So, for example, if I have these other two, right, with 2 arrows, well, this could actually, if I do the free construction, could actually give me something which has got an infinite amount of arrows, because there is no guarantee that when we compose stuff, we get back to ourselves. This is something that we will see later, which relates to the concept of isomorphism, which I will not go into it. But this is kind of an idea of how you should think about categories. You have identity arrows everywhere, and you can, whenever you have 2 arrows, you compose them. So these are very artificial. They don't relate to anything interesting as far as I know. I don't really know, because I just came up with them on the spot. So if they relate with something interesting, cool. But yeah, so anyways, let's really talk about interesting categories. So categories that pop up somewhere else in mathematics. And the first one that we're going to talk about is the category of set. So as I mentioned before, this is the prototypical category. Like when we work in category theory, you can quite a lot of the time say category things which are defined in set, express them in terms of arrows, because remember it's all about the arrows, and then just replace those arrows with general morphism in categories. So it's fine. So what does the category of set have? Well, as I mentioned before, as objects, yes, sets. So any set that you can conceivably think on is in an object, and in a function. Well, Well, sorry, yeah. I gave away the punchline. And an arrow, oh, I decided not to cancel anything. Cool. I'm gonna write it down here. So an arrow is just a function from A to B, is just a function from A to B. And you can see that the notation that we use is actually exactly the same as what we do when working in set theory, so this should seem very natural to you. And of course, composition is just the normal composition of functions. The identity of a set is just the identity in the categorical sense. So everything is just exactly what I was talking about, just abstracted away, well, concretized, because before I gave you the abstract setting and this is the concrete setting. What's another kind of thing you may ask? Well, this is one of my favorite ones, and that's groups. So as objects, we have all the groups. So for example, here you might have, I don't know, you might have the client for group, you will have SN, you will have, I don't know, Z 2021, all these kind of groups. And as arrows, well, I'm just going to put some dots here because there are a lot of them. Just for fun, the monster group is in here somewhere, just to show you complicated things. I mean, it's not really, it's just a group at the end of the day. Okay, and as arrows, well, an arrow from, we could technically use, you know, all possible functions, because that would give you a category, because composition still works, you have identities, that's fine. But we don't particularly like that. Like, as I said, in category theory, it is all about the arrows. So you want your arrows to kind of propagate some of the properties of the object that you have. So in this sense, if we were using all the functions for this kind of thing, you would really just get like a smaller kind of group, right? Well, not even, because actually you would just get a copy of group, because every set can be made into a group, like with some trickery. So well, it can actually be made in a cyclic group. So you have a copy of set into groups. So that doesn't really help you that much. What we really want is something which propagates the structure. And if you ever done group theory, you will find that the right kind of concept that you're thinking about, it is group homomorphism. So what are those? So group homomorphism is a function that goes from a group A to a group B, yeah, which preserves the group operation. So just in case if you're completely new to group theory, I apologize because I should have said this sooner. But a group is a set which is equipped with a group operation. So given any two elements, you can multiply them together and get another element of the group. And this operation also has inverses. So if you have G, there is an element G inverse that when you multiply with G, you get the identity of the group. And the identity, of course, is the element that when you multiply it with all the other elements, it just gives you the same element. So this is kind of the idea of group theory. I will not delve too much into it, but the idea is that a group homomorphism is just an operation which preserves this composition. So if I have X and Y in A, we need to satisfy the property that the product gets mapped. So we have this exact property, right? And what's important to note is that here we are using the multiplication in A, and here we are doing the multiplication in B. So this is the kind of idea of how you preserve the structure, because whenever you have an homomorphism, essentially you're just defining a copy of your original group, kind of similar depending on injectivity and all this kind of stuff in the other group. So that's kind of the idea. And of course, you will find that the identity is a group homomorphism, and you will find that the composition of two things, of two homomorphism, is also an homomorphism. The proof is tedious, I will not go through it here. So this kind of thing is actually quite general, because you can actually extend it to a lot of other things. So for example, You can do it with rings. In this case, the objects are rings and the arrows are ring homomorphism. You can do it with fields, even though fields is a horrible category for reasons, well, because essentially there are no arrows between between fields which have a different characteristics. So it's a very boring category. It doesn't have any of the nice construction that set or group, for example, have. So it's very boring. So a lot of categories that you deal with, for example, there's one of vector spaces and all of that, just take a normal kind of mathematical construction, and they make it the category in which the objects are all the objects that satisfy the construction, and the arrows are homomorphism between which preserve the structure. So that's kind of a way in which you can get a lot of categories. I'm going to actually talk about another one. So there's for every group we can actually associate a category to it. How to do that? Well, let G be a group. So we can make a category which has got like one single object, and it has one arrow for each element of G. So I'm just gonna draw it for. I'll actually draw it for K4, right? So this will be the arrow corresponding to the E element, to the A element, the B element, and the C element. And if you don't know anything about the client for group, so write K4. This is a multiplication table. It's quite straightforward. I'm just gonna quickly fill it in. So then we have that every element has got order 2. So on this diagonal, everything is E, and then you can check that just putting C here and completing essentially gives you everything that you need. So this is the multiplication table of the client group, and you'll notice that we can actually use this and just we can just define association. So I'm actually going to just put some little notation here. I'm just going to put some things over here to denote. So we'll have that HC is the arrow associated to X in the group, right? So I'm just going to use that as notation. And we can define the group, we can define the association operation for this category by having that, sorry, I'll just do, does it cancel? I will just do X, Y is equal to X to the composite of that. So this is kind of how we can, well, we're actually using, I'm just gonna do a little bit like this, right? So, and the idea is this construction is generally enough that you can do it with any kind of group. So for any group, you can get a category with one object, which is the group. You know, it's just the group as a category, which is quite interesting. You can actually even think about mapping. Well, later on, we could actually think about functors between these between these one object categories, and just a little bit of thing just gives you these functors are exactly the same as group homomorphism. So this is just something which I wanted to give you an idea of some other kinds of categories. And this is actually some example of something that you do a lot in category theory. So you think about things on different levels. So for example, one interpretation that you might have is that a group is an element of the category of groups, but it also is a one element category. And you can think of the category of groups as both the category with groups as its element, and both as the category of functors between one element groups. So a lot of different kind of abilities. So by switching this kind of like levels, you can get a lot of interesting structure, which is interesting. But anyways, I have digressed a little bit, so sorry. Let us talk about another one, but let's go. So as I was saying before, there is one category which we're going to be talking about most of the time today, and that is the category of Haskell types, which we denote to as Hask. So Hask has got, as always, the objects are the types in Haskell. So I'm just going to write that down. And the arrows are function between types. So I don't know, like a function which goes from A to B. I'm not sure about the exact syntax, but something like that should work. And first of all, I have to make an obligatory note, which is that Hask is not really a category. That's because that's because of the undefined, which sometimes we also refer to as bottom, and which is written like this. And essentially, the core idea is that when we have undefined, a lot of things stop working. So, for example, we can show an example in which identity composition does not. Sorry, the composition with identity does not hold. That if we have stack bottom unit, which is equal to undefined, and then if we have stack of bottom followed by ID applied to unit, which is equal to unit, which implies that, of course, undefined followed by, sorry, ID followed by undefined is not equal to undefined, which is, of course, that's a violation of the identity axiom. So technically speaking, Haskell is not a category, but it looks damn well like it. So it's got a lot of similar things to it. It looks very similar to set, for example, because he has, because types can kind of be thought about set if you squint hard enough. So for a lot of things and for a lot of application, we like monoids, monads, and all of this, it really helps to consider Haskell as a category. And if you still feel unsure about this, I suggest there is a paper which is called Fast and Loose Reasoning is Morally Correct. I'm just going to write the title down so you can have a look. Is morally correct, which just explains why not caring about undefined is a completely legitimate strategy. So that's something that you might have a look at. And yeah, so Hask is the category we're going to be looking the most at. For a lot of purposes, it really helps to think about it like set, but then not really, because if you think about it, there are some kind of functions which are in Hask and they are not in set. So for example, if we think, for example, the set of all Turing machine as we'll have a function which tells it whether that particular Turing machine holds, and of course that's not a computable function, so it cannot be expressed in Haskell, while it is a function in category of set. So Haskell is like the category of set if you look at normal stuff, but if you start to kind of look at these kind of things, you show that it's not exactly the same thing. But that's something else that we won't look too much about it. But just another example, right? So let us talk now about isomorphisms, which are something that we're going to be needing for the definition mostly. Not something that you really need in the Haskell sense, but it will be very helpful for when we have to talk about natural isomorphism and all this other stuff. So isomorphism come from the Greek same shape. So the idea is that two things are isomorphic if they have the same shape, the same structure. So for example, if we have two element sets, A and maybe B, so these are sets with one element, they will be isomorphic, which we write this way, because even though the sets are not technically the same, they have the same exact structure, right? So if so essentially they just look the same. Like there are some differences, but there are not those that we care about. In the same way, if I have like the set 0, 1, 2, 3, and the set, I don't know, E, A, B, C, this will be isomorphic because they all have, even though the elements inside have different names, you can actually map one to the other with a bijection. So that's kind of the idea of isomorphic. And note that isomorphisms are quite interesting because you can use them to say which kind of objects have some differences which are worth caring. And what do I mean about that? Well, for example, like this isomorphism is what we call an isomorphism of set. So there is a set isomorphism between them. But if we look like these two sets are the element sets of two groups that we've seen before. So 0, 1, 2, 3 is the element set of Z4, and EABC is the element set of K4, the Klein 4 group. And we know that these two are not isomorphic as group because, for example, K4 has got 3 elements of order 2, while Z4 has only got 1 element of order 2. So essentially, they're not the same thing, really, in groups, of course. And so at each level at which you look at objects, the isomorphism tells you which other elements are similar to it. Okay, so it's all well and good, but how can we define them in general settings? Well, it's actually quite simple. We first do the usual trick that we do in category theory. We take something, we put it down in set, and then we just change from function to arrows and from sets to objects. So I suppose we have A and B, which are sets. What are the requirements for A and B to have to be isomorphic? Well, intuitively, you would need of them have the same size. But of course, as Cantor showed some time back, having the same size works very well for finite set, but once you start talking about infinite ones, it starts being a bit more difficult. So essentially, the definition that is more robust is that there exists what is called a bijection between them. So I'm just going to write that down. So there exists a function from A to B such that f is a bijection. And now, okay, so this is already quite good. How can we translate this notion of a bijection into general category? Well, we would like, first of all, we would like to see instead what does it mean to be a bijection. And in fact, set is a very nice category, almost too nice in this sense, because it can lull us in a sense of almost too much security. So let's see. So there are two equivalent definitions of bijection in set. So I'm just going to write it like this. If and only if. So either F is injective and surjective, which I'm not going to explain what they are right now. I'm just going to make a remark about it. Or F as inverse. So this is kind of the characterization. And I'll just make this note around it. The concept of injective and surjective morphism translate quite naturally in category theory as well. To the injective becomes monomorphism and surjective becomes epimorphism. But what's interesting that in general category, we have that epi plus mono does not imply iso, which is instead something that we have instead. So if we have a function which has an epi, well, instead the epis are just the surjections, the monos are just the injections. So in set, mono and epi is a bijection, which is an isomorphism. So that's all fine, good, but that's not something which happens in general categories. So don't. It happens in a lot of categories, but not in all of them. So there's not something that you wanna use that much. What we really would like, what we really need for a isomorphism is this part here. So that F as an inverse, and we can have a look in what it would mean in set. So right, so F as an inverse. Let's call this inverse G. So we'll have A, B, A. So this is F. An inverse will go from B to A, and it needs to be that their composition is equal to the identity on A. So this is equivalent to saying that GF of A is equal to A. And similarly, you can do that on the other side, but we'll do that on a more general term. So definition now, we can translate this very naturally. Let A, B be objects in some category C, which I don't know. We will first say that f from A to B is an isomorphism if and only if, since we're doing a definition, there must exist a G from B to A such that the following two things are satisfied. So as again, we're gonna just do the diagram so we are sure that our arrows are the right way around. So A, B, A, and then B, A, B. And there we are. So this is F, this is G, and this is G, and this is F. And we will have that GF is equal to the identity on A, and FG is equal to the identity on B. So these are the two conditions for isomorphism. And you can see that these are general, they don't rely on a structure on set, but they still are able to encompass the notion that we had in set. So this is something that we do quite often. We take something which is in set, and then we replace arrows with functions, functions with arrows, and set with objects. So that's the kind of transformation that we do very often, and we'll see it later doing it in Monoid. So this is the definition of an isomorphism. In fact, you can check that if F is an isomorphism, then G will also be an isomorphism, which also makes it everything into which just makes everything very nice. So just an idea. And we can have a couple of examples. I'm just going to write a few. So if we have in set we have bijections are iso. In group, that we have that what's it called? In group, that we have that group isomorphisms are iso, which is good because if it weren't, there would be a very bad naming scheme, which happens sometimes in mathematics. Iso in top. So top, I haven't talked about it too much. That's the category of topological spaces, and arrows between topological spaces are continuous functions. And we have that homomorphisms are iso. And this is quite interesting because that's one of the cases in which it isn't enough to have bijective homomorphism. So in fact, an homeo is a homeo between A and B is a function from A to B such that F is continuous. It has an inverse G, and sorry, F is continuous. It is also bijection, and it has an inverse G such that G is also continuous. So we need injectivity and surjection, but we also need the inverse to be continuous, which is a stricter condition. So this is one of the cases in which the mono and epi break down. So just thought I would mention that. Now, let us move ahead boldly, and we will start by talking about functors. So, did you write it? Perfect. So, what are functors? Functor, in the same way that there are maps between groups, map between rings, map within set, functors are maps between categories. So what do? Well, we've seen before that group homomorphism respect the structure of the group. So we would like to have the functors respect the structure of the category. So let's consider two categories C and D. A functor from C of D, which we write like this, consists of essentially two mappings. So you will have a mapping on objects. So you will map an object A into an object FA. And then we'll have a mapping on arrows. So this mapping on arrow needs to be compatible with the mapping on objects. So essentially, if I have an arrow A and AB, sorry, an arrow from F from A, B, this will be, I'll just write this to see what it's mapped to. It will be mapped to FA, FB. So it will be mapped in an arrow FF, which has as origin FA and FB. And it is kind of confusing at first because FF, so because the notation is used the same for object and arrows, but everybody does it, and I fear them up, as one wise man once said. So this is what a functor is defined as. So he has to have he has to have these properties, and in addition, he needs to respect the operation of association. So we will have to have that, first of all, that identity is respected. So if we have the function, if we have the functor of another identity, it will be the identity of the mapped object. And then we have to respect composition. So if we have f of gf, right, it will be f of g times f of f, where here we're using the composition in C, and here we're doing the composition in D. So this is what a functor needs to do, and yeah, that's the kind of idea. And to give you some intuition, I'm just gonna draw a category and then maybe some two small categories and then maybe some functors between them. So I'm just gonna take something like this. Of course, if we have those two, well, we have those two, we also need that. And this might be mapping to another bigger category. So I'm just gonna write it like this. I'm gonna write some nice functors maybe. So this maybe has this, which also means he has this. And of course, I'll drive some of these identities. So a functor will, for example, one functor could map this to this, this to this, this to this. This edge then will have to be mapped to this one. This edge will be mapped to this one, and this edge will be mapped to this one. So that's a very messy diagram, but that is the kind of thing which a functor does. In particular, the one which I drawn is an injective functor. So it essentially draws a picture of the category into the other category, and those are very, very useful. Yeah. So this is not a very natural one, but now we will see one which it is. So we will be looking at this thing, which is what we call an endofunctor. So endofunctors is just a functor where the target and the source category are the same. So it's a functor from C to C. And this will be very, very useful because as we will see, those are just the functor that Haskell has, because Haskell calls their functor, but they're not really functors, they're just endofunctors. So they cheat a little bit there. And we're going to be looking at one in particular. So we're going to be looking at the power set functor, which goes from set to set. And this is a very nice functor because first of all, we will show how it acts. So on objects, you will map a set A to P of A, which is just the power set of A. So just in case you're not familiar, this is just the set of subset of A. Yeah. So this is the set of all the subsets of A. So in general, if A has got n elements, then the power set of A will have 2 to the n, because there are that number of ways to choose it. So that's the power set, and then we'll have that on arrows. So let's take two sets A and B, and a function f, and then this will have to be extended to a function from the power set of A to the power set of B and we'll denote this by PF, right? So how can we do this? Well, there are some ways. The most natural one is just to define PF to be the function that, given a subset U, so U is a subset of A, will just compute the image of U, which is clearly a subset of B, since F is a function from A to B. So that's one of the ways we can do it. So now we can verify that it is actually a functor. So we verify. Let us first verify the identities. So let A be a set. Then P of 1A is the image is equal to the image of 1A. And of course, if you do P of 1A of any subset U, then you will get the image of U, which is just equal to U. So he acts, so essentially you can see that he acts exactly as the identity on 1A. So P1A is equal to the identity on PA. And well, now we will we'll show the respects composition. So let's take a commutative diagram. So we'll take the following: A, B, and C, and then we'll take F and G. Then we'll have that P of GF is equal to GF image to the image of GF, and just a little bit of set theory, which I will not do because it's a bit tedious. Well, not even tedious, it's just not very insightful. They will show you that this is the image of GF composed by the image of G, and that is exactly equal to P of G times P of F. So this shows you that this is a valid definition for that functor. This is a nice one. I like it because it gives you some intuition on what it might be, and it's also useful for natural isomorphism, homomorphism later on. But let's show one which is a bit more pervasive. So in particular, we're going to be talking about the hom functor. So we're going to be looking at hom R. So where? So this is a functor from some category, C for set, where R, well, just first note that this C cannot actually be any category. It needs to be a category which is something called locally small. But in particular, all the categories that we introduced so far are locally small, so don't worry about it too much. So where R is an object of the category C. So what does this functor do? Well, on objects, hom R A is the set of all functions from R to A. Okay, cool. That's yeah. So just maybe take a second to internalize this. So this is a way to take an object and take all the arrows into it. And how does it work on arrows? Well, let's consider the following. So let F be let F be an arrow from, say, X to Y, right? So I'm just going to write it actually like this. Then we will take yeah, that's what I want to do. So this will be mapped to an yeah, so from R to Y, so OY, so this is just the hom of RF. And how can we do that? So we would like to take an arrow from R to X and turn it into an arrow from R to Y. Well, we know that F is from X to Y, right? So we can just define hom RF to be the function that takes any kind of G, so let's call it G, and just return FG. So that's how you define it. So this is essentially just a functor which that composes the stuff. And yeah, and this is often hom RF is just written as F, I think, top star. I'm not completely sure, just for convenience, but that's the idea, that you just compose and that's the way that you can get an arrow from R to Y, because of course this will be decomposition. And there's this Ohm functor is extremely powerful. It is in fact, it's probably one of the most important things that you can use in category theory. The Uneda lemma is based on this essentially, and a lot of other stuff. But it has quite a lot of structure. For example, it is actually a bifunctor because it is functorial even if you are choosing the R. But we will not go too much into it. But just wanted to give you some example of some interesting functor. And something that we will. I don't want to spend too much time onto this, but in fact, functors form a category. And this is something that we will need later on for monads. But first, I have to introduce something else. And those are natural transformation. So what are natural transformations? Well, natural transformations are essentially the easiest way to talk about them is as morphisms between functors. So I think the easiest way is just to go with the definition, and then I'll give you some examples and try to tell you why they're important. So let's consider two functors which have the same source and target. So let's have f and g are be functor from C to D. Then a natural transformation A from F to G, that's how we denote, is a collection of arrows. So, which we will just call alpha C for C in the category C, and each alpha C will be mapping from FC to GC for little c, of course. So this is how it is. And in addition to this, we will have to satisfy a certain what's called the naturality diagram. So given anything, so this this is in C and this is in D. So suppose we have the following arrow in C. So let's call it XY. Then this arrow will be mapped by the two functors into these two arrows here. So this will be f of x, this will be f of y, and this will be f of f. And this will be g of x and g of y, and this will be g of y, of f. So these are the two things. We can now use the arrow that we have in the natural transformation. So we have to have this, the following one. So this will be alpha of x, and that will be alpha y. And the naturality condition is that whichever way you navigate this square, you always get the same result, which in symbols is written by GF alpha x. So I'm just going to put some parentheses on it, is equal to alpha y FF. Some parentheses. So this is the kind of thing that we require for a transformation to be natural. And now, first of all, we want to talk about why it is a natural thing. Well, if we think like if we think about preserving structures, right? The idea is that you can have a lot of arrows between x and y. Like think about any two sets. There can be infinitely many arrows between them, but we're only allowed to select one arrow for a natural transformation. So if we have, I'm just gonna make another diagram because I don't want to pollute that one. So suppose we have a lot of arrows going from x to y, right? Then this will be mapped to another lot of arrows. Well, some of them might be mapped to the same one, depending on the functor, but that's not something that we want to talk about. So we will have a lot of them between the two functor mappings. So this is the one mapped by F, and this is the one mapped by G. But we are only ever allowed to choose one alpha for the two objects. So a naturality condition means that this alpha is so natural, so well defined that it is able to work for all these kind of this kind of error that it might be. And in some sense, it does not need to make any arbitrary choice. This is very apparent if you think about vector spaces. I will not make the example directly and write it down because it needs a bit of contravariant functors that we don't really need, and I don't want to talk about them. But essentially, if you think about the double dual of a vector space, it is trivially isomorphic to it because they have the same size. But it is also naturally isomorphic because you can define one evaluation kind of map, which is able to map between the two of them, and is an isomorphism. While if we think about a vector space and its dual, so not its dual, just its dual, then they are still isomorphic because they have the same size, but they're not naturally isomorphic because in order to define an isomorphism, you need to pick a basis. And in general, the vector space isomorphisms need not to preserve basis. So the choice that you make is very arbitrary. And so there is no canonical way to do it. So that's kind of the idea of why why these are called natural transformation. And yeah, I'm gonna just give you an example using the power set functor. So we will consider these two functors. So there is the identity functor on set, and there's the power set functor. So these are, as you can imagine, they're functors on set. The identity functor, I haven't defined it, but essentially it just does exactly nothing. So it maps every object to itself, and it maps every arrow to itself. So it does really nothing. And we will show that there is a natural isomorphism, a natural homomorphism alpha from one set to P. So, okay, let us take an X, Y, and F in set. So we're gonna just map it. So this will be exactly the same because identity functor does exactly nothing. And then we will be mapping with the power set. So this is the P of F, the power set of X, and this is the power set of Y. This is, of course, the power set of F. So we need to define some alpha X that maps from the power set of X. Sorry, from yeah, right. I cannot. Okay, we need to define an alpha X that maps from the power set that maps from X to the power set of X. Sorry, I haven't had enough coffee today. And how can we do this? Well, one idea, which of course there are a lot of functions between them. They could even be infinitely many, but the most natural one is just the following one. Well, for me at least, it's just the function that maps A. It maps it to the one element set with A. And now we claim that these arrows, which are defined this way, are natural isomorphisms. So first of all, intuitively, they're natural because you don't need to assume anything about the structure of X and Y, and this thing will just work. But now we show that the naturality condition actually is preserved. So let us write those in the diagram. So this is alpha X and alpha Y. So we first check, so we take P of F alpha X, this is equal, and of course the two functions are equal if and only if all their output on a certain input, sorry, if their output is the same for the same input. So we're just going to take an element of A, so I'll just, of X, sorry, which I'll just call A for similarity. So this will be equal to the power set of F applied on A by the definition of alpha X. This is just the image of this, which is just a function of the image, F of A image. So that's just very natural. And then if we do it on the other way, then we'll have alpha Y applied on of F of A. So this is just the F of A again. And since these are equal, and since we made no assumptions on F, this will hold for all F from X of Y. And so alpha is natural. So this is the kind of idea that we can exploit. And in particular, I'm gonna just make a passing note. We also have the concept of natural isomorphism, which is essentially alpha from F to G is a natural isomorphism if alpha x is isomorphic. So is isomorphism for all x. So that's the kind of idea. So if you have a natural transformation in which all arrows are isomorphism, then it will be a natural isomorphism, which this is also works very well if we talk about the category of functors with natural transformation, because that's exactly what it is, but let's not go into that right now. Note, for example, in this case, there is from one set NP, it is not a natural isomorphism, and in fact there cannot be one, because then there will be an isomorphism between a set and its power set, so they would have the same size, which of course, unless the set is the empty set, is a contradiction, because any non-empty set will not be the same size as its power set. So that's just a couple of things. Yeah, I will not show a natural isomorphism because we won't need it right now. Well, there are some, but well, we can show one later on with natural transform. Well, with while we're introducing nets, which are the universal mapping properties. So, what are universal mapping properties? The idea is that again, in category theory, everything is all about the arrows. So, if we have so there are some kind of properties that we usually define by ways of talking about the objects, which can be very well translated into category theory. In particular, we're gonna be looking at 4 of them, which, sorry, I'm gonna just title the page. We're gonna be looking about 4 of them. So we're gonna be looking about initial object. We're gonna be looking about terminal objects. We're gonna be looking about products and sums, which we will also call coproduct for something else that we're talking about. So again, let us take an example in set. What's an initial object in set? Well, an initial object in set is the empty set. So the empty set is very special in a set. For example, as I said before, it is the only set which is isomorphic to this power set. But that is not a very good definition to base it on. Something that we might note is that if we get any other object, then there is always one map from the empty set to that object. So if there is one unique map, in fact, so because so it's f from alpha to any alpha exists and is unique. And this can sound like nonsense to you, because how can you define a function that goes from the empty set to something else? Because it takes no input and gives you no output. Well, essentially, it is very trivial. It is a very stupid function, but it exists, and there is no way to define another one, because you know, it takes no input, so you cannot choose which kind of output you give it to it. So that's kind of the idea, and we can generalize it to any kind of category. So we will have that an initial object 1 I is an object, so that for all other object A, there exists a unique, which I use an exclamation mark to it, a unique f that goes from I to A. So that's kind of the idea of an initial object. Okay, a terminal object is an initial object. Well, it's an initial object in the reverse category. So what is that? Well, essentially, there's a very powerful concept in category theory, which is that of duality. And that concept is that you can take any category, just reverse all of its arrows, keep the object the same, and then you'll get another category. That is because all of the axioms of category theory are symmetric between source and target. So that's the kind of idea that we would like to use here. And so whenever we have a definition in category theory, we can just turn all the arrows around, or even when we have a proof in category theory, we can turn all the arrows around and get another proof for a dual fact. So this is the concept of duality. we can do the same thing for terminal objects. So we'll just like for all A, there exists a unique F, sorry, such that, so we will call the terminal object T, and I'm just going to call it T, A. So there is a function from A to F. So that's kind of the idea. What's a terminal object in set, you might ask? Well, any kind of one element set is a terminal object in set, because if I have any other set into this terminal object, we can just define a function f of x, and there's only one choice that you can make. So you will have to map to that element. And something which is interesting here is that while the initial object was actually unique in set, because in set there is only one empty set, there are actually infinitely many different one element set, but they're all isomorphic. And that's a very important thing of category theory and of universal mapping properties in general. Universal mapping properties essentially are only categorize elements up to isomorphism. So if two elements are isomorphic and they have the same unique mapping property, then they will if two elements have the same universal mapping property, then they will be isomorphic. That's the kind of idea. And that goes back to our before, when I was saying that you only ever care about the arrows. So in particular, if two things are isomorphic, they have all the same arrows coming in and out. So it makes no sense to distinguish them. They cannot have different properties from the lens of view that we are looking at. And yeah, so these are universal mapping properties. And now we're going to be looking at two which are more important. So, well, not more important. The initial terminal objects are very, very important, especially if you do higher one, but they are very, very simple. And here we're going to be looking at a more complex one. So again, let's look in set. In set, we have the product of two elements, of two sets A and B is just the set of elements of it. So it's just A and B such that A is in A and B is in B. So that's very well and nice, but how can we do this just in terms of arrows? Well, there is a very nice universal mapping property for this. So we can just take, we can say that a product is consists of three things. So sorry, a product for A and B consists of three things. So we have one object which we will denote by A and B, and then we will have two arrows which will go from A and B to so we'll call this the projection of A, and this will be the projection of B. So these are the three things that make up a product, but we also have to satisfy the universal mapping property, which in our case is that if we have any other object which has the same shape, so in this case that it has got the projection. So I'm going to just write A. I'm going to rewrite this down here. Right, so this is projection of A, and this is projection of B. If we have any other object which has got the same shape, and I'll call it X, for example, and I'll call this G, so F and G, then there must be a way there must be a unique way to map X into A of B. And then, so I'm going to write it as dotted to say that it is unique. And then the two diagram needs to commute. So essentially, if you first take this unique arrow and then you take the projection, it must be equal to applying F. So this is the kind of idea. I will not spend too much time talking about why the product is that in set and doing this definition. It is actually very easy, as a lot of things in category theory follow straight from the definition. So don't worry about it. And we can go next with A plus B. So A plus B in set is just the disjoint union. So I'm just gonna write it like this. And it satisfies exactly the same properties, but it says they are reversed, again, by the concept of duality, which I was talking about before. So this is just, instead of product, I will call them injection of A and injection of B. This is of course A, B, and then A plus B. And for any other object of that shape, you will have the unique arrow. So just gonna write the diagrams. I of A, I of B. Oh, sorry, this actually is the wrong way around. There we go. Sorry, this doesn't allow me to erase, which is very, very annoying. I can only erase the whole page, and I don't want to really do that. So we can go like this. Then we will have F, G. We'll call this X, and this is A plus B. This is A, and this is B. So this essentially is the exact thing as the product, but we turn the arrows around. And in fact, this is often just called the coproduct, which is nice, admittedly. So this is what the universal mapping products are. And in particular, we will be using them because now we will be starting talking about monoids, monoidal categories, and all of that. And the product and the coproduct are very natural ways to define monoidal structure on category that you have it. In fact, if we think about Hask, the monoidal structure is given by the product in a certain sense. Then there are some subtleties with currying, but we will not look at them too much. So next up, we're going to go to talk about monoidal categories. So first of all, to talk about monoidal categories, it first really helps to know what a monoid is. So a monoid, in my opinion, is the simplest kind of abstract mathematical structure that lets you do useful things. So let's go with the definition, which is very simple. So this is a monoid in set, which is, again, we're going to do the usual trick. First, do it in set, express it in terms of arrows, and then change in terms of functions, and then change the functions to arrows. So easy like that. We're going to do the usual pattern. So a monoid is a set. It composed of three things: a set M, an operation which will denote by dot, and then a unit which we will denote by E. Where I'm just going to write for completeness. M is a set. This is an operation from the product of M to M. So it takes two arguments and it gives you one. And this gives you closure automatically. And then E is an element of M. And this will be the identity element. So I'm just going to say set of elements, operation, and this is the identity. And you need to satisfy the following two axioms. So we will have to have the identity axiom. So if we have for M in M, we have that ME is equal to M, which is also equal to E times M. And then we also will have associativity, which is just that A, B, C in M implies that A, B, C is equal to A, B, C. So these are the two conditions that you need for monoids. And those are very, very simple. You can take some examples. So for example, my favorite personal one of a monoid is a binary string. So if we take the following triple, so we have the set of all finite strings, we have the note that we're also including the empty string, then we have the concatenation as the binary operation, and we have the empty string. This is a monoid. It also works with list and anything like that. Of course, groups are monoid because groups satisfy, they have an identity, they satisfy associativity, they also satisfy having inverses, which is a more strict property. So in general, they are monoids. So rings are monoids. A lot of different things are monoids. So and the one. So now we're going to be doing the first real math part, which is we're gonna try to take this definition and express it by only using arrows and sets. So first of all, let us let us start by looking at what the three things that we have. So M is just a point in the in set, right? So that's fine. Then an operation, sorry, the multiplication is just a function from, I'm just gonna write it as mu instead of the dot just because it looks a bit better. It's just a function from that to M. And now what is the identity? Well, we know that the identity is an element of the set. But of course, if we're doing categorical stuff, we cannot look inside that. So we need to find another way to do it. And if you think a little bit about it, you will note that you will note that any element of a set can be thought about as a function from the one element set to that set. And that's kind of like, yeah, that's, I'm not even sure how to talk about it directly, but the idea, it is a bigger thing. So it is vehiculated by an isomorphism, which I don't really want to talk about, but essentially it is in the same way that when you talk about in Haskell, right, and you think about constants, they are really a function from the unit type to some other type. So that's the kind of same thing. So what we can do, we can express the identity as a function from the one element set, which in this case I will denote by 1 into M. So this will be E. And in fact, if you want to look about it, this is actually part of a bigger isomorphism that's mu is equal to M is equal to is isomorphic to that, and it's actually isomorphic in a natural one if you do the correct morphism and you take care of the right kind of and if you take care of the right kind of contravariance and all that kind of stuff. But let's not dwell into that right now. I mean, actually, we could. Let me just have a look if I. Yeah, this could actually work. Okay, I'm going to take a pause from this categorization, and I'm going to just show you that this is actually a natural isomorphism, just because it's cool, and I can actually get to show you some natural isomorphism. So I'm just going to take a little break and prove this. So remember, like that. So M. So remember that when we're talking about natural isomorphism, we like to talk about isomorphism between functors. So what we really need to show is that there is an isomorphism between the identity on set and the Ohm functor which goes from the one element object to something, right? So you're gonna take a set, let's say A, B, and a function f. It will be mapped exactly the same as before with A, B, F, and then this will be mapped to the arrows from 1 to A and to the arrows from 1 to B, where this will be, as I said before, F with the composition. So now how do we define an alpha A such that it maps from A to the Ohm of 1A? Well, this is actually quite simple because we can just take a function which takes an element of A. So let's call it, yeah, I really shouldn't have used the lowercase later, but anyways, just takes x as an element of A, and he mapped it to the function that takes anything, really. Oh. That takes, let's call it just asterisk, and he returns x. So this will be the thing that we're looking at. And so now we can draw it. And that's alpha A and it's alpha B, right? We can show that it is actually natural because if we take, so it is natural and we can show it because we have that alpha A followed by F star, right? Applied to A, applied to X is equal to F star, which is composed by the function which takes literally anything, and it just returns X. And this is equal to the function which takes literally anything, and then it returns the f of x, if I remember correctly, and if I got the order right. Then we can do the same thing on the other side. If we have alpha b, if we have alpha b followed by f, this will just take, if we apply it on x, this will just be alpha b of f of x, which will be just the function which takes anything and returns f of x. These are equal, and so we know that alpha vinculates a natural transformation from one set to the homomorphism of one to this. And now we just need to show that these are isomorphisms, but this is kind of obvious because if you look at alpha A of alpha A as an inverse, which we will just call B of A, which goes from one to that, and then beta alpha and beta A is just A just takes a function f which goes from 1 to A, and it just evaluates it. So and we can show that this is an isomorphism. So alpha of one set is isomorphic to alpha of one. I just use this as an element of one, just for thing. Anyways, so this is just a nice proof and shows you some kind of a natural isomorphism, which sorry, just came up with it. I should have done it earlier. Hopefully that doesn't give you too many problems. Anyways, let's go back. So now we know that a monoid has got the following three things in a set. So it's got M, an arrow from M times M to M, and it's got an arrow from 1 to M. So these are the three things that we need for a monoid. Okay. Now we need to find a nice way to express the naturality condition, sorry, the associativity and the associativity and the identity condition. So first, with associativity, we can just start and looking at that. So first of all, if we have an element, if we have three elements, then we're gonna have to consider the product of three things. And there are two ways of building this product, right? You can take either the two on the left and then the one on the right, or the two on the right and then the one on the left. So we're gonna just call it M, M, M. So we're gonna have this, and then we're gonna have M, M, M times M. So these are the two. And in fact, instead, there is another isomorphism, which is natural between the two, which will be quite nice, but I'm just gonna put it down there. Now we're gonna be using this function, which essentially just takes multiplicates with just this, sorry, which takes the first two elements, multiplicates them together, and then it does nothing with the third one. So this will take the first two and produce an element of M. So this will be M times M, and we're going to do the same one around here, only that we're going to do it on the other side. So this will be 1 times mu, and this will be also giving us an element of M of M. And then finally, we can just compute again, just by applying mu again, and do M. And associativity is equivalent to saying that these two things are the same. So you might be wondering why we are using that notation of mu times 1 or 1 times mu. That's because actually the product construction is also functorial, so you can think of those as other functors, but don't worry about it too much. It's fine. It's fine. Like kind of, yeah, these are like bifunctors, but we won't do that. But this is the kind of thing that we need for the associativity. And now we're gonna do identities, because those are very nice as well. So we're gonna think, okay, we want to get a pair which has got one element which is the identity and one element which is an element of M. So there are two ways of doing that. I'm gonna do both left and right at the same time, just because it looks very nice on a diagram. So we're gonna just do this. So first we're gonna take the initial set, and then we're gonna take the product with M. So we're gonna take an element of M and the only element of the one element set. We are gonna apply, well, there's a, yeah, we're gonna apply the unit one, which here I will call, I'll just go back on top and call it N. So this will just do N times the identity. So we just don't do anything else. Now, there is another natural isomorphism, which we're gonna be using here, which just maps this into M. And it's essentially what it amounts to discarding the one element set, because if you think about it, it doesn't really do anything. Like if you have a set of size 5 and you take the product with a set of size 1, then you still get a product of a set of size 5. So you don't get any more information. So naturally, like you can just don't care about it. It's kind of like the same thing exactly. So they're the same size, so they're isomorphic. So you can do that. And now we can just, this will be an element of M times M. We can just take the product by mu, and that will work. And in particular, we can actually do the same thing on the other side, only that we'll have it on the other way around, right? So we just use our isomorphism. I'm just going to put it because it's an isomorphism, so it can go both ways. And then will be 1 times mu. And if you take the pain to actually feed values through this diagram, you will see that these are exactly equivalent to the condition that we saw before. Only that instead of using sets, we just use arrows, which is very, very nice, because now we can lift this to categories, which is exactly the same thing which we're gonna do next. So that's gonna be very, very interesting. What's the intuition for this? Well, the intuition is that the product in set really works well. So in set, if we have M times M times M, it is isomorphic to M times M times M, which is the thing that we saw before. It also has that M times 1 is isomorphic to M, which is also isomorphic to M, 1 times M. So the product that we have on set really does a lot of things similar to the monad, to a monoid, sorry. So essentially the idea is that, like, look, we working in set is very nice, but we would like to be able to work with other categories in general which have this kind of structure. And the way that we do that is by generalizing the monad thing with endofunctor. So that's what we're going to be doing exactly now. So monoidal categories, those are, so monoidal categories are categories which has got some kind of functor on them, so some endofunctor, which has the same nice properties that the product has on the inset. So that's what we're going to be doing now. Let us start very, very nicely. So it is a triple, so we will have a triple C. We're going to still be calling it mu. No, we're going to be calling it this, and then we will have some initial object E. So these are the three things. So where C is a category, right? Oh, I'm actually gonna use the product instead of the sum, sorry. So is an well, it's not an endofunctor, it's a functor from the product category, so from C to C up into C. And then the initial object is an object in C. So These are the same thing. You can verify that this is just what I took before with the monoid. I just replaced C with M, really. And it just works exactly the same. So cool. And in addition to that, we have to satisfy some identities. So I'm going to say, and the following old. So we will have an associator, which is a natural isomorphism, which will denote by alpha. They just vehiculate this isomorphism. So just going to write it below, just so the structure is a bit nicer. So the idea is that you can build the functors by combining functors, and essentially here I mean that I'm meaning an isomorphism between functors which take a lot of arguments. So essentially this is a very, very nice functor. But think about it that there will be arrows A, B, C that just simply do this isomorphism, right? So yeah, so there will be these arrows, and these will also have to satisfy some niceness condition, but we will not work too much about them, so don't worry about it. And other than that, we're gonna have to satisfy the identities, and so we're gonna have those were called the left and right unitor, which are just two natural transformations with which do the following natural isomorphism. So, and this will be a row. Oh, sorry, I keep writing the wrong stuff. So, and this might all look very, very fucking scary. Sorry, I shouldn't have swore there, but very scary. And essentially, this only means that this is just a translation of what we had before with monads, only that we had translated it in the language of functors. So that's just exactly the same thing that we had before. And yeah, unfortunately, it's kind of hard to wrap your head around it, especially when we're talking about natural transformation, which have got more than one element, more than one argument. But don't worry about it too much. All that it means is that you have something which behaves very much like the product in the category. Essentially, we need to define this because later on we will see that applicative functors are functors that there are functors which behave nicely with respect to this with this kind of structure. So in the same way that a group homomorphism will respect multiplication, and in the same way that functor respect association, as applicative functors, or also called monoidal functors, will respect this monoidal structure. But that's something that we'll see later. First, okay, that's very interesting. But now we can use actually the diagram, and we can define the general term of a monoid. So a monoid in a category now. So this is something that we do again. This is exactly, we can take the diagram that we had before, and we can just use the monoidal structure and the arrows to define that, to define whatever to define the concept that we want. So we're gonna have a C be a monoidal category. Then monoid in C is a triple which has got M mu, and I'll call it, sorry, let me check my note to see how I call it. There we are. Yeah, I call it. Sorry. m, mu, and n, such that then we will have m is an object in C. Mu is a function from the product. In this case, we use the monoidal structure from up into M, and then mu is a arrow from one from the identity object, well, the unit object into M. So this is the it was a bit unnatural of me to first define what a monoidal category is before defining what a monoid in a category is, because a monoidal category is actually, if I remember correctly, a monoid in the category of categories, maybe. Yeah, but in order to define what a monoid is, I had to define what a monoidal category is in order to give you the structure that you need then. So I tried to avoid the circularity as much as possible because I felt it wouldn't really help. And yeah, so anyways, so this is what a monoid is, and it also has to satisfy the properties as before. So we have to have associativity, which again, we do with the diagram as before. So we will have, I'll just write them little because you have the bigger one around there. So we'll have m times m times m is equal to m, right? So wrong way around. Oh man, I'm awful. Okay, I'm gonna go in the next page. Just at this point, why not make it a bit more clear? So m. If I do it on the right or I do it on the left. Now, as we saw before, we have an isomorphism, which is the associator isomorphism. So we can just put it in here, right? So this is the association isomorphism. We can now use the identity and mu, same as here. We can use mu and the identity. This will be m times m, and this will be m times m. And now we can just put it together by using mu. So that's the same thing as before for associativity, right? Now we can do identity in the same exact way as before. So we have IM. This will be by theta times 1. Did I call it like that? Yes, I did. We will get some element of m times m. Then we can just multiply and get an element of m. And here there will be the other unitor thing, which I was talking about before, which in this case is the left unitor. So I'd call it lambda, right? And then we can just do the same thing on the other way. I'm just going to call it lambda, and I used rho here. And this is just m times I. Here we'll use I, and that's exactly it. So these are the same. This is just identity. So by just doing this, we just talked about what a monoid in a category is, which is very, very nice. So in particular, we can just look at about in set. So for example, in set, it is very obvious to see that a monoid in set is just a monoid. And defining different categories, you can have different monoids. You could, for example, even endow set with a different monoidal structure, and then your monads, your monoids would change a little bit, but we will not explore that too much today. I just wanted to give the idea, because now we're going to be looking at one example in particular, which is one that people will love. Well, I don't know if people love it, but it's definitely a word which is thrown around quite a lot. What's a monad? Well, a monad is just a monad is just a monoid, but in the category of endofunctor. So I'm just going to write that monoid in category of endofunctors. Okay. So, okay, I need to actually give you some stuff before we go. So, first of all, we will have that there is a. Okay, let me just take everything. I just want to check my notes a little bit before I go into this. Okay, yeah. I didn't really write too much on it, but I'll just pause a second. Okay. So, okay, let's start. Let C be a category. Then we can have a lot of then we can look at the endofunctors of that category. So F from C to C. We will show that we can actually have a category, which is the category of endofunctors on this. So the category as we'll have as objects. We will have those endofunctors as arrows. So an arrow between an endofunctor. So I'm just going to write something. This is called a path diagram. So these are just F and G. These are two endofunctors in this case because they go from the same one. An arrow between them will be a natural transformation, and we can verify it as a category. I would have to talk about the composition of natural transformation, but it works exactly as you expect. In fact, there is a little. In fact, the category of functors has a little bit more structure on it. It's what we would call a two category, but let's not go in it. Just know that you can actually have arrows between arrows, and then arrows between arrows between arrows, and then so on. And at the end, you get these things which are called infinity groupoids, which are, well, infinity categories, which are very weird. So we will not go into there. I am not entitled to talk about it because I don't know anything about it. So just throwing terms around here. But yeah, just know that the category of functor is a very nice category. It's got a lot of structure, and you can have a monoid in it. So first of all, we will have to have a monoid in a category. We need to give it some monoidal structure. So how do we do that? So we do this thing by composition. So we define some functor, which we'll just call this, which goes from, so the category of functor is often defined or denoted by CC. So is the text two element of CC. Yep. This product is just the product of categories. So just bind with me, and it gives you another one. And how it is defined? Well, we define it by FG is equal to FG. So we just compose the two functors. And I will let it as an exercise to decide what it will actually do on arrows. It is not obvious, but you have to chase some community diagrams, and it will help quite a lot. So, anyways, then let us see what let us now unwind the definition and see what a monad is. So, a monad in this category. So we will have M, we will have mu, and we will have neta. Oh, sorry. Before talk about it, the identity object E is equal to the identity on C, which is very obvious because you will see that the naturality just follows very, very quickly. In fact, I think this is actually a strict monoidal category, I think. Yeah, I think it is a strict monoidal category, but don't worry about it too much. And yeah, so a monad in this category has got like M, which since it's an object of the category, is an endofunctor from C to C, right? Mu is a mu is an arrow from mm up to m. So this is actually an arrow from m squared to m, just for convenience. And then we will have that n is just an arrow from the 1, which is just one c, up into m. So in fact, these are just natural transformation, right? So is it actually a natural transformation? Yeah. So these are just what these things are, right? So arrows are just natural transformations, and we can use them. We could actually expand everything. So I'm gonna do this now by just taking my diagrams and expanding them. So I might have been digressing a little bit, but we will be fine. I mean, we're not going to rush anyway, are we? So what are the other required things? Well, we will have that the associativity condition, which I didn't actually write like that last time. I'm just going to write it like this. So we will have that m getting 3 elements. So m squared times m, and then m times m squared maps to mu times 1, and then 1 times mu. This will actually be m squared, and this will be m squared, and this goes into m. So, and these are all, of course, natural transformation. There's actually a natural isomorphism. In fact, this might actually be the same object. This will probably be the same. This will be the same object. Sorry. So we have to have that this commutes, so that there are this natural transformation, which essentially, yeah, this is essentially what we need. And then we'll have the triangle equalities, with just that if you take m, there is a natural transformation to m squared by times I 1, and then we can just keep going with these things. This will be m again. This will be the one that we are guaranteed to have by, this actually is 1c times the product, and so on. We can do the other one. So this is kind of like how you get a monad. I don't want to spend too much time because I won't touch it. It's just an application which I like quite a lot. And in fact, you can actually derive these things very easily. You just really unwind the definition, which is why I don't think it's very instructive for me to talk about them. I hope I haven't made too many mistakes. So now for the next part, we're going to be talking about monoidal functors. So again, as I was giving you the idea, is that a monoidal functor is a functor which preserves the monoidal structure. So let us go directly from the definition. So suppose we have these two categories. So we have C, which has got this monoidal structure, and D, which has got this monoidal structure. So these are two categories, doesn't matter what they are. This is a very generic definition. And we say that F from it is a monoidal functor if, first of all, F is a functor. So this is a very important thing. And in addition, you will have to have two natural transformations, which are, right in it, satisfy the following properties. So we have one natural transformation is this. So remember how before I was this is essentially, you do the same exact thing with group, but instead of requiring equality, you use natural transformations again. So you will have one transformation, which I call like this, which just takes the following. This is actually the opposite way than what I usually like to do, but This is how I saw it in the literature, so I thought it would be better. So it will be this natural transformation, which in fact means that on AB, you will have a map from FA product FB up into F of A times B, where of course you use the monoidal structure of the two categories. So that's how you tie them in. And of course, you need to also play nice with identity. So you will have to have an arrow, which is called psi, which goes from the identity of D up to the functor of the identity of C. So these are the things that we need. And also we will have to have this transformation play nice. So the idea is that we would like them to be as nice as possible, to play, to interact with each other in the most natural way possible. And that's what we're gonna do. And there are essentially two things that we wanna preserve. There is associativity and right identity. So I'm just gonna write, we want preserve associativity and right left identity. And the idea is that actually you also have some leeway on how strict and how lax you are with this kind of thing. So some definitions only require natural transformations. Other ones require natural isomorphism. Some of them actually require equality. It depends on how much leeway you want to give. I'm going to just give the most relaxed definition possible as always. So the first one is we want to be able to preserve the associativity. So we would like that the following diagram also. So this is essentially what we did before, but we just are using the monoidal things. So I'm just going to take this. Well, there are two ways that we can do this. So we can first apply f of a, b together with 1, and this will actually bring the a and b together. So this a times b till time f of c. Then we can apply it again. I'm just gonna, and this will just, in this case, we will actually apply f of a times b c. This will just give us f of times b beta c, right? We can do it in the other way around, which is the same exact thing, but on the other side. So we will have f times b times fc. And here we can apply 1 times alpha bc. Then we can apply, and this of course will give us f of a times f of bc. And then we can apply it again by just on the other side. This will be a, b, c. This will give us f of a times b, c. So this is the two ways that we can do stuff. How do we relate them? Well, we can use the monoidal structure of the monoidal structure of D, which allow us to conclude that there's an isomorphism here, which is given you by theta of the theta of D. That gives you the isomorphism. And now you can check that by taking F and applying it on the alpha of C. This also gives you an isomorphism because functor preserve isomorphism, which is a very easy exercise. So you can, that's how you put them together. And if these play very well, then you actually have preserved you have a preserved associativity. So this is the idea. Then we're gonna do the same thing with identities. I'm gonna do right identity first. So this is actually just a square. So we're gonna take f of a times the identity of D, which then we can actually map by using 1 times the function that we had before. We can map it by f of a times f1c. Now we can apply the alpha, sorry, the theta, the phi, which is A IC, and this gives you f of A times IC. So that's one way you can do it. The other way, you can apply the right identity of D, which of course just gives you f of A, which then you can apply the right identity of C reverse, because it's an isomorphism that gives you f of rho C, and that needs to play well. And of course, you can do the same exact diagram, which I'm going to briefly do here, by just using left instead of right. No, the direction of the arrow doesn't actually change. Left and the right is just, yeah, just cosmetic, really. It's like it is inside the order in which you do them. So I'm just going to very quickly do it. It's just the mirror of the other one. C I C A. This is just f of lambda C. This is f A. And this is just lambda D. So this is the, oh, this is right ID, and this is left ID. So essentially, this is a very horrible and scary diagram, but the intuition that you should have about it is that we want, not only we want to preserve the product and all of that, but we want to preserve it in a nice way. So we want to maintain the associativity properties, and we want to maintain the identities properties. So that's why we go through all of this effort. And let me just check here. Do we need anything else? No, not particularly. Okay. Now we can just tie it all back in, which is nice because it took me a long time to do all of this, and see how does it relate, this relate to Hask. So first of all, I'll preface saying that, like, while I've written some Haskell, I'm not the best at Haskell. So we will try to see it from a more categorical perspective. I don't expect you to become a better programmer by just looking at this, but it's just quite nice. So first of all, in order to work with these monoids, this monoidal structure and all of that, it's very nice to give Hask a monoidal structure. So again, with the caveat that we said before, that Haskell is not really a category. We can squint, say like, look, I don't care about undefined. It looks very much like a category. I'll just work with it anyway. So that's what we're going to do, and we're going to give it a monoidal structure. So give monoidal structure to Hask, right? And we can do that very easily. So Hask is so we're going to create it. We're going to give it. So we're going to have that the multiplication operation is just given by making a pair out of it. So we'll just call it this, and then I'll just write what it is. And the identity will just be the unit type. So it will be the unit, and this will just be theta AB is equal to AB in the classical way. So that's essentially, we're just using products very, 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 very easily. So first of all, then we remember that Haskell functors are really endofunctors on Hask. And there we are. So that's now we're gonna see why. Now, okay, the endofunctors on Hask. So we're gonna just look at the difference. So if we have a real endofunctor, then we have an object mapping, as I was saying before, which just goes from A to FA, and then an arrow map, which just maps AB to the following diagram, right? In Haskell, we just do the morphisms map, because in fact, if we know the types, it just the type completion is good enough to actually infer the one on the morphism, and you don't really ever need to map the morphism, the object and much. And we do that via the F map, which is actually very naturally, it just maps a morphism AB to a morphism F of A. So I'm just going to call this Haskell functor F, from F of A to F of B, right? And this is exactly the same. It is exactly the same idea that we had before with functor. So here I'm just doing the same thing, all I'm doing in Haskell notation, which is very, very nice. But okay, this is very simple. But now let's talk about applicatives. Applicative functor. So in particular, we got, since again with the caveat that functors are endofunctors in Haskell, this is really an applicative endofunctor. And in particular, we're going to be preserving the same monoidal structure. So remember what we're going to have? So we're going to have three parts. So first of all, we have the functor part, because every applicative functor is a functor. Then secondly, we're going to have a map, which goes from the identity to the functor F to the functor of the unit, let's say. And then three, we're going to have a natural transformation, which goes from theta, so we call theta, and goes from F times F and goes to F. There we are, like this. And again, in here we are talking about things in Haskell, so really this operation is the same, and it is the element of taking pairs. So in Haskell we will have the following three things. So we will have, first we will inherit something from functor, right? Secondly, we will not, in functor, we will have that E is equal to the unit type. So a map of that with that signature will be a map from unit up to F of unit. So this is actually will just be an element theta of F of unit because of the isomorphism that we saw before. Finally, this natural transformation will, we can first take it evaluated at two types, A and B, right? And so this will be a function from F of A to F of B. They will map that to F of A, B. So this is the kind of thing that we will be looking at. And how can we define that? Well, we will define, in fact, I probably didn't say this before, but what we will define now is a class, a type class called monoidal, which is not exactly the same thing as applicative, because essentially when we are talking about monoidal functors, as mathematicians, we like to think of them in the most natural way possible to preserve the monoidal structure. But that's not the most efficient way to implement them, because you need to implement a couple of things. While we need to implement a couple of things which are not they're not a priori obvious. While if we're working with Haskell, there are some ways which we'll deem more natural to implement. So in this case, we will be defining a type class, which we will call the monoidal type class, and then we will show this is equivalent to the applicative definition, and that will conclude everything really. So we'll just do it. Pardon if my syntax is not perfect, so we'll just do class functor F. And just before I say this kind of the proof that these two are equivalent is I borrowed it from Bartosz Milewski. There is a really beautiful Stack Overflow post in which he talks about this. So anyways, so class functor F is a monoidal functor where we have a unit, which is just an element of the F of something, and then he has a multiplication which just takes a pair FAB, FB, and just gets FAB. So this is exactly condition 3. And now we're going to look at the applicative one definition, which is just applicative F, which oops, sorry. class. I'm going to go in the next page actually, because I always forget the syntax. So class functor f is an applicative functor where we will have a pure, which just gets an element of A and it gives you an element of FA, and then mult, which gives you, which takes, which is exactly the same thing. In fact, in Haskell, this is sometimes written a little bit differently, but we will not care too much about it. Anyway, so this is the definition of applicative. Now we will like to show that pure and unit are the same thing. This is actually quite easy to do because pure x can be defined to be f map of const x unit, and then unit can be defined to be pure of unit, because essentially what pure and unit are is already can be determined by the other one by just exploiting the functor structure we already have. And you can take some instances and check that these are completely equivalent ways of doing that. And so this was how we can get applicative functors from category theory with a little bit of a caveat. So in summary, this has been my talk. I hope you enjoyed it. This took a lot of work to prepare, but it was actually very fun. I like it. And I feel category theory is one of these topics which really present themselves very well to presentation, because all the definition, all the rules are something which come very natural. So in fact, it is something that you can almost come up with as you're doing the presentation. I had some notes to help me just to figure out what the most natural were, but it isn't that hard. Like, it's something that you can sit down 1 hour with some pen and paper and then just scribble definition and they will be right. So, which is very beautiful. That to me really speaks to how natural and beautiful the theory is. So I hope you enjoyed it. I don't have an audience right now, so I cannot take any questions, but just pop me a message if you feel like there's something which needs to be changed, or if you have just some questions about category theory in general. There's a lot of beautiful things here. I might do some other videos later on, but for now, this has been all. This has been Giacomo, and you've been a fantastic non-existent audience. But anyways, I hope you enjoyed again. So thank you.